Hello, it's Keith here, and this is lesson 63 of the platform-specific series of my 6502 assembly programming tutorials. And today we're going to be looking at sound on the Apple II, as you can probably see from the title. I've also got an oscilloscope above me, which always gives you a clue we're working on sound. What we're doing today is we're writing my new and vaguely improved ChibiSound Pro driver. The ChibiSound driver was designed for little bleeps for a Space Invaders type game. ChibiSound Pro is more geared towards simple music and things like that because it allows for multiple channels, multiple volume levels, a wider range of pitches, and still the noise effect that we had before. It also includes a lookup table of the correct pitch values for the notes of the octave for that hardware, and that's what's used for the music playing. So we're going to be using this today on the Apple II. Now the Apple II has super simple sound, which I will refer to as beeper sound. Basically, we only have one thing that we do. All we need to do is do a read from the port C030, and this will cause the sound wave to invert the outputted sound wave. And so by doing this repeatedly at the right times, we can create some kind of beep. The problem is that we will need to use the CPU power to correctly time these and make the beeps, and of course we've only got one sound channel. So we're kind of treading the line of between bravery and stupidity by trying to play music on it, but we're going to try all the same, and don't expect too much is all I'm going to say. Now, with regards to the ChibiSound Pro driver, this simulates the Z80 functionality because it's originally a Z80 program. So the H entry in the 0 page will be the channel number, bit 0 to 6 only. Bit 7 is the noise on and off state for that channel. The L value is the volume. That's an 8-bit value now, just 1 bit before, it's now 8 bits. And the DE pair, 16 bits, is the pitch, and we will pass that to the hardware in some way. Now, on this system, what we're going to basically have to do is we're going to have to time the correct amount of time for the pitch between the times that we send a value, or read a value, sorry, from C030 to build the wave. So the shorter delays, the faster the changes, the higher the pitch, and the longer the delays, the lower the pitch. Of course, we can only do this for one sound channel. What we're going to do is we're going to simulate multiple channels, and the ChibiTrax sound program is going to tell the hardware, I want to set this channel to this value and this channel to this value. And then what the driver is going to do is going to take the loudest of the channels that are supposed to be playing, and it's going to use the beeper to play that current sound. That's how we're going to sort of compromise to get around the limitations of the hardware. Anyway, let's go over and let's actually hear the driver in action. So first of all, we're going to run this very simple sound test program here. So we'll just fire this up here. So you can hear there's a beep here, and then if I use the joystick here, as the number changes here, the pitch will get higher, and if I press fire, we've got a noise effect there. So that's just a test of the functionality of the sound driver. I've got the delay rather long there. If I reduce the delay, the the joystick would actually move between the values faster. But I've set it very long here for when I was testing the frequencies for the frequency table, because the longer the delay, the clearer the frequency was for that software. So that's why that's there. Anyway, don't expect too much, but we can then use this to play some music. So this is a little music file that I created before. The important thing with ChibiTrax is the binary music files don't need to be recompiled for the destination system, so that this original file was compiled for the Amstrad CPC on the Z80, and it can now play on the 6502 without being recompiled. The binary is identical. So here we go. So you can hear, we've got the tone and we've got simulation, if you will, of the drum effect here. As I say, it's hardly incredible. I'm not going to claim that's the best music that mankind has ever heard. However, considering the limitations of the hardware and considering we're basically simulating an AY sound chip, as I say, the music was originally designed for the AY sound chip, then I think we've got something at least worth considering. You know, this is what I was able to get working on this system in the time available. Okay, so the first thing we'll have a look at here is the Chibi octave. Now this is a lookup table of 16-bit values for the various frequencies for a range of octaves and the notes in the octave, and you can see the frequency values marked above each value here. These are the correct frequencies. I used a frequency analyzer program to get the correct ones for the notes. Now these are the pure tones. If you wanted a sharp or a flat, you would basically take two values, add them together and divide the result by 2 to calculate the between value. That's what the ChibiTrax program does. Now, when it comes to this program, as I say, we're going to have to simulate multiple sound channels that don't exist. So we're defining a cache, and we're going to support up to 4 channels, and that's because the ChibiTracks program expects at least 3. As I say, it was based around the AY capabilities, which is a 3-channel system. So we're going to simulate 4 channels in the channel cache. We're also going to have a byte for the noise position. Now, to make noise, what we basically do is, rather than flipping the wave every time by reading from CO30, we occasionally miss it based on a single bit noise value, if you will. And what we're going to do is we're going to use the byte code of our program itself as a random noise data. It's not truly random, but it's random enough. And so we will have a 1 byte value from 0 to 255 for the offset for our noise source there. We've also got a tone length entry. Now this is special for the beeper systems, because basically for the music to continue playing, we actually need to use processing power to actually keep making the tone. The tone won't make itself. We have to use the CPU to do it. This is not true on most systems, but on these beeper ones it is. And so the longer the tone for each iteration, the more CPU power we're using. So if we're doing nothing but playing the music, like the example today, we maybe want a quite long tone, but if we were trying to do something else at the same time, like, you know, maybe on a title screen, we're cycling some colors or something, or doing a little bit of animation, we'd want the tones to be shorter so that we can use the remaining processing power for other stuff, but the music will degrade in quality accordingly. Now we can actually try this out. Now at the moment we were using a tone length of 4. If I change this to 16 and run again, the music will become slower, but the quality will become a little bit better. This is far too slow now. I think we need to change our delays maybe. But as I say, you can see that in principle here we can actually increase the length of the tones, and we will get clearer notes. There we go. So I've changed there was a delay in there. Basically reduced that to 0 now. And the tones will sound a little bit clearer. As I say, it just depends on how much processing power you've got and what you want the music to sound like. But that is what our tone length is for, and we can use this special function, set beeper length, on this beeper system to set the tone length as required by our music and our processing power available to us. Okay. Now, at the start of the initialization routine, the first thing we're doing is we're clearing the ChibiSound RAM, the cache, and we are initializing the tone length. We're loading 16 here and then falling into this to store that 16 here. So the default tone length is going to be 16, but as I say, the test I was running earlier, it was just 4. The ChibiSound Pro set routine doesn't do a whole lot. It loads in the value in the L entry in the 0 page, and it takes the bottom 2 bits. This is the channel number from 0 to 3. And we then multiply this by effectively 4, and now it becomes an offset within our channel cache. We then write the H, L, D, and E entries into the channel cache for that virtual channel. And that's all we do. We then return. Now, every single iteration of our music, we have to run an update. This is only for the beeper systems, and what this basically does is it plays whatever note, gets the CPU to play whatever note we want to play for this iteration. Okay, how are we going to do that? Well, what we're going to do is we're going to basically find out what the loudest channel is, and it's the H entry that contains the volume. So we're loading H to 0 at the start, and we're going to sequence through the channel cache, and if we find a channel with a louder volume than the current one, which will be the first one, definitely will, because we started from 0, we're going to load in the H, L, and what were D and E, but we're now moving them to B and C here. The B and C, the D or D and E, these are the pitch. We're flipping the pitch. We're doing an EOR here because we need the lower the frequency, the deeper the tone, if you will, the longer the delay needs to be. And so I'm actually flipping these around, because by default a value of 1 passed to the ChibiSound driver would be a very low pitch note, but now we want that to be a very high pitch note. So we're flipping the bits in that 16-bit pitch value there, and we're storing the results in B and C here. Now we're repeating this until we get to the end of the cache. 4 entries, 4 bytes each, 16. And so when we get to this point, we've actually got whatever the loudest channel was, if there was any channel playing at all. Now, because we can't do volumes, we're basically ignoring anything that's below a volume level of 16 here. If that's the case, we're just assuming that this is a silent tone, so we're not going to make any sound at all. Now, in the case that we are doing nothing but playing this sound, i.e. we're not running this through an interrupt handler, we actually need to have a delay here. So we need to simulate a delay because, as I say, the CPU will be completely being used by making a tone, so we need to completely use it for when we're not making a tone so that the music plays at a consistent speed when there's silence. So we've just got a delay here. This deck B, deck C thing here, this is just a 16-bit delay for when we need to wait for a moment, and here we're waiting for that silent tone, if a silent tone is such a thing. Now that's what we're doing there. What we're doing next here is we are checking the top bit of the L entry, and that is the noise state. That's going to be a 0 if the noise is off, and it's going to be a 1 if the noise is on, and we're transferring that to X for later. We're then increasing the byte offset of the noise source, the random data source, and we're storing that in Y. So X is if our noise is on or off, and Y is our offset. Okay, so there we go. Now, what are we going to do next? Well, what we're going to do is we're going to transfer our BC pair into some values that we can actually use for our loop. Now, we'll come back to those in just a moment, but what we're going to basically do is we're going to need to do a loop, and we're going to need to flip the waveform by repeatedly reading from CO30. That is the only line that actually makes a tone. So that is the line that makes a tone, and the important thing is the delay after the tone. Now, we're using B and C as our delay, and we're running it using this ChibiSound pause routine here, which is the same one as was being used by the silence. So this is the delay between the flips. The longer this delay, the lower the pitch, and the shorter the delay, the higher the pitch. And so that pause here is responsible for defining the pitch. Now after that pause, we're jumping back up to here, and we're making the tone again. Now, we're going to continue making that tone for a period of time, and that period of time needs to be roughly consistent in all cases. So what we're doing here is we're actually subtracting the high byte of the pause from the H entry, and the H entry is the tone length. So we need the D and E entries here because they're being transferred to B and C for our loop each time. We need those to be an appropriate value for the pitch, for the delay to make the pitches. And so, as I say, a very high value will be a very low pitch because it's a very long pause. A very short value will be a high frequency, a very tight waveform. So that's what we're doing here. And so basically what we're going to do is we're going to take the 16-bit HL pair that was passed to us in a pitch, and we're going to shift them until we basically end up with a 16-bit pair like this. So basically almost all of the top bits are 0, and we've only got effectively a 10-bit value here, which will be the length of our pause in between flips with the CO30 entry there. So that's how we're doing our pitch, and how we're using this tone length, and we're subtracting the top byte of that pair to calculate when we need to finish making the tone. And that's so the tone is roughly the same length, whether it's a very high pitched note or a very low pitched note, which is important if we're playing music, because we can't have low pitches taking a long time and high pitches taking a short time. But I should point out that it's not exactly precise here. I mean, I think you need some kind of interrupt timing to make it more precise maybe, but as I say, it's reasonably adequate. It was the best I could get working. So that's how we're defining our pitch. But what about when we're doing our noise? Well, all we're doing with the noise is occasionally we're skipping this command. So all we're doing is we're transferring the X register, which is either going to have a top bit of 1 or a top bit of 0, to the accumulator, and we're then ANDing it with a byte from our current program. And so this will basically set the top bit to either a 1 or a 0, but if the noise is currently off, it will always be a 0. Now, in the case that top bit, which if the noise is on, sometimes it will be a 1 and other times it won't. If it is a 1, we're going to skip this command. And so this is basically always running this command if noise is off, and it's running this command randomly 50% of the time approximately if the noise is on. And that's how we're creating our distorted tones. A bit weird, but it does work. I mean, some of this, it kind of sounds so stupid and so simple that you wouldn't quite believe it could actually create tones, but as I say, it does. And while they aren't amazing, they are adequate, and you can even I've not done it on this system, but on the ZX Spectrum, which is the same beeper technology, you can even play wave files with it. You can play speech samples if you want, just by timing this correctly. Anyway, there we go. So that's how today's example works. So if you like what you've seen, please like and subscribe. And of course, you can go to my website and download today's example. If you're interested in this music thing, please consider backing me on Patreon, because as part of this, I've also been writing this Chibi Tracks music software, and I don't get to make videos about that, so there's no real revenue source for me to continue doing that. So for me to justify spending my evenings writing the music software, I have to gain Patreons who are backing me to continue working on it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.